Hello everyone. In our previous lecture, we have introduced the topic of logarithmic mean temperature difference, and we have seen LMTD for both parallel flow as well as counter flow, and we have seen that LMTD for counter flow is greater than LMTD for cross flow is greater than LMTD for a parallel flow heat exchanger. Now let us see there are two special cases regarding LMTD of heat exchangers. There is one of the cases that when one of the fluid in heat exchanger is undergoing phase change, that is a latent heat of one of the fluid is utilized either to increase the temperature of the other fluid or to decrease the temperature of the other fluid. Let us say, let us take the example of steam condenser. This is the diagram for parallel flow and this is for the counter flow. One thing you can observe that THI and THE are same, and THI and THE are same irrespective of whether it is a counter flow or a parallel flow heat exchanger. And the final temperature, therefore, since the THI and THE are same, the final temperature achieved by the cold fluid is also same in both the cases. Let us write LMTD for both parallel flow and counter flow and see whether they are same or not. Before that, let us take T for THI and THE. Okay, since both THI and THE are same, we are giving this a new letter, that is T. Okay, let us start writing the LMTD for both parallel flow and counter flow. In case of parallel flow heat exchangers, what is happening? Let us solve for parallel flow first. In case of parallel flow, hot fluid will be at high temperature T and cold fluid will be flowing from TCI to TCE in the same direction. Therefore, delta Ti is nothing but T minus TCI. Always remember that inlet should be the inlet of the hot fluid. Here also inlet is the inlet of hot fluid. Okay, delta Ti is nothing but T minus TCI. Delta T is T minus TCE. Therefore, LMTD is nothing but delta Ti minus delta Te. After simplifying, we will get this TCE minus TCI by ln T minus TCI by T minus TCE. In case of counter flow heat exchanger, since the inlet should be the inlet of the hot fluid, this is our delta Ti should be this one, difference between this. Delta Te must be different between this. Therefore, delta Ti is this written, delta T is written. Delta Ti minus delta Te, that means TCI minus TCE you will get, and in the denominator we have T minus TCE by T minus TCI. This is, if you take out minus from numerator and minus from denominator, we will get LMTD parallel, which is therefore LMTD counter is equal to LMTD parallel. How can you take out minus from here? Just write the upside down. Take this to the numerator and take this to the denominator. Then you can multiply with negative sign. Therefore, with this we have proved that LMTD parallel is equal to LMTD counter when one of the fluid is undergoing a phase change. Our previous example is for the steam condensers. If you are talking about the steam generator, here the colder fluid is undergoing phase change. No matter which fluid is undergoing phase change, if either one of the fluid is undergoing any phase change, then we have LMTD parallel is equal to LMTD counter. Therefore, from now onwards, only one thumb rule: if it is given that any of the fluid is undergoing a phase change, then LMTD is same for any type of flow. Either it can be a parallel flow or it can be a counter flow. The examiner need not mention it in the question. This is very much important because the students get confused in the examination and feel that the examiner has not given whether it is a parallel flow and counter flow and will not solve the problem, and finally he will lose the marks. So this is very important point that one should note. And the second case is that when both the hot fluid and the cold fluid have same or equal heat capacity rates. If you remember, we have already solved a problem on this concept. It is given that m dot HCP is equal to m dot CCP. Therefore, by applying energy balance, we will end up with delta Ti is equal to delta Te. Upon substituting this in Lmpd equation, we will end up with 0 by 0, which is undefined. Upon application of L'Hospital rule, we will end up with Lmpd counter flow is equal to delta Ti is equal to delta Te. This is very special case for counter flow heat exchanger. One should remember counter flow heat exchanger. This is possible only with the counter flow heat exchanger. Sometimes a new name will also be given to this case, like balanced counter flow heat exchanger, where the temperature profiles will be parallel. That is, this is THI, this is THE, and this is TCI, and this is TCE. Throughout the length of the heat exchanger, temperature profiles are parallel. Therefore, it is called as a balanced counterflow heat exchanger. If you want a neat diagram, I will show you that also. Here the neat diagram for balanced counterflow heat exchanger. Throughout the length of the heat exchanger, temperature profiles are parallel and straight lines. Till now, we have seen what are the different types of heat exchanger, how actually the heat transfer will take place. Now that finally the time has arrived to design the heat exchanger. Design of heat exchanger is nothing but the calculation of the number of pipes required, number of passes required, length of the heat exchanger that is required, diameter of the tubes, all these things that we have to calculate depending upon the amount of heat that has to be either extracted or supplied depending on the heat exchanger. Let us see this question in a problematic manner. There will be some data will be given. That data can be mass flow rate of both hot fluid and cold fluid will be given, and specific heats will be given, and overall heat transfer coefficient will be given, and three among the four temperatures will be given, and we will be asked to find the area of the heat exchanger. Since we know that both the heat capacities are known to us and three among the four temperatures are known, we can find that fourth temperature very easily by applying the heat balance equation. Now let us draw the temperature profiles. By listening the word temperature profile, don't get any confusion. It is just the lines which we use to draw. That's it. Whether it is to identify whether it is a counter flow or parallel flow, it is only for the simplification of the problem and easily collecting the data. Okay. After that, we have to calculate the heat transfer rate. That is, Q is equal to m dot HCPH into THI minus THE. You can use either of these formulas and calculate Q. And we have another formula for Q, which is UA delta Tm. Since we have already calculated delta Tm from after drawing this diagram, and we know the value of Q from these equations, we can find the area since U is already given in the question. Now after finding out the area, just write area is equal to pi dl into n, that is number of tubes into number of passes. From this you can find anything you want. We will also solve some problems on this. Okay, you have to calculate the dimensions of a tube from the area of the heat transfer in heat exchanger. Generally this type of questions are asked in ESC. In GATE he will not go into this much depth. Anyhow, let us cover this topic also. Area is nothing but surface area of the tubes, that is pi dl into n into p. Passes, number of passes, one should be clear with number of tubes and number of passes. Number of tubes is nothing but number of inlets or number of outlets. Number of passes is nothing but how many times the single inlet tube or single outlet tube is turned inside the heat exchanger. Let us see this. Here a single tube whose inlet is here has an outlet here, therefore it has made 2 times its length is 2 times that of heat exchanger, therefore number of passes are 2, and number of tubes here are 3 only, not 6. Since the number of inlets are 3 or number of outlets are 3, therefore number of tubes are 3. Number of passes is nothing but how many times a single tube has a length is equal to the length of a heat exchanger. How many times the length of a single tube is greater than that of the length of heat exchanger, therefore number of passes are 2, number of tubes are 3. And one should always remember that while writing the mass flow rate, one should not consider the number of passes, therefore you should not multiply with P, because only the same fluid is entering here, it is passing through here, and going out, therefore there is no fluid entering additionally into the tube in the second pass, that is here, from here, therefore whatever be the mass entering here, that is only going out here, therefore you should not multiply with number of passes. Therefore the formula for the mass flow rate is density into cross sectional area of the tube into number of tubes into velocity, and you should not multiply with number of passes, therefore we should not multiply with P. Okay, we should not multiply with P. Let us see the effectiveness of heat exchanger. Effectiveness of heat exchanger is nothing but the ratio of actual heat transfer to the of maximum possible heat transfer. This formula we have already seen in case of fins, but there we have named it as efficiency, and effectiveness in case of fins is nothing but Q actual upon Q without fin. Therefore in case of fins effectiveness is greater than 1, but here effectiveness is nothing but Q actual upon Q maximum possible. Since Q maximum possible is the maximum amount of heat and Q actual should be always less than Q maximum possible, therefore effectiveness is always less than 1 in case of heat exchangers, and in case of fins effectiveness is greater than 1. Q actual possible is nothing but this formula which we have already seen. Q maximum possible is m dot Cp smaller into Thi minus Tci, since this is the maximum possible temperature difference within the heat exchangers. Therefore we should always remember that with this we should multiply with m dot Cp smaller only, because we cannot multiply with m dot Cp larger here. This is very much important, please make note on this. M dot Cp smaller, M dot Cp larger or nothing. These are comparison of M dot H Cph and M dot C Cpc, out of which whichever is smaller, that is called M dot Cp smaller. Out of this whichever is large, that is called M dot Cp larger. In this formula you should substitute whichever is smaller of this. Either it can be M dot Cph, M dot H Cph, or it can be M dot C Cpc. Practically, if we see, the effectiveness of heat exchangers are generally between 0.55 to 0.8, and if m dot H Cph is less than m dot C Cpc, then this is the smaller one, and effectiveness can be written as the ratio of Q actual upon Q maximum possible. While writing Q maximum possible, we have to write m dot Cp smaller. Since m dot H Cph is smaller, we have written this, and this is the maximum possible temperature difference. And here there is no restriction, you can write anything you want. either m dot h cph thi minus the or m dot c cpc tce minus tci. There is no restriction here, but there is restriction in this formula that I will tell you later. Let us say if m dot c cpc is smaller one, you should write it in the denominator. This is mandatory, and since the maximum possible temperature difference is thi minus tci, this is always be there in the denominator, and in the numerator there is no restriction. You can write either m dot h cph into thi minus the or m dot c cpc tce minus tci. But if you are writing this formula, again there is restriction. This formula is for simplicity. While writing simplicity formula, one should make note that both in the numerator and the denominator there is a same heat capacity rate, so that it will get cancelled out and you will end up only with the temperatures. Let us say if you are having m dot h cph as a smaller one, if you are writing m dot h cph in the numerator like this, these two will get cancelled out. You will end up only with the temperatures. Similarly here also, these two will get cancelled out. You will end up with temperatures only. So you cannot use both of these formulas simultaneously. It depends on the values of heat capacity rates, which one is smaller, which one is larger. Therefore only one of the above formula, that is one of the either these two simplified formulas for effectiveness, is valid at a time under the special case of both the heat capacity rates being equal. Then only any formula can be used. Since if both the heat capacity rates are equal, you can use any of the formula, you will get the same result. Now let us see the concept of number of transfer units, that is NTU. There are generally two methods to solve the heat exchanger problem. One is Lmpd method and the other is Ntu method. So we have already discussed Lmpd. Let us discuss this Ntu method. Ntu is nothing but number of transfer units is equal to UA upon m dot cp smaller. This is very much important, where U is the overall heat transfer coefficient, which is equal to 1 by h1 plus 1 by h2, provided there is no fouling on the pipes. If there are fouling, then we will add f1 and f2, where f1 is inside fouling factor and f2 is outside fouling factor. That I will explain when I am telling you fouling factors. Okay, and let us see this. Here the fluid is flowing inside, which is hot. Because the temperature difference, there will be a convection heat transfer here, and there will be conduction inside the steel tube or a tube of a heat exchanger, after which again there is a convection outside. And I have already told you that in case of heat exchangers, we are not considering the resistance due to the heat exchanger tube, because the size of this tube is very thin. Therefore we can neglect the conduction resistance from here. Okay, let us discuss something that is related to fouling factor. Fouling factor is nothing but while the pipe is in service, it will get some deposits over here as well as on the outside, that like any chemical deposits or scaling will be there. So to consider this resistance into picture, we will consider fouling factor. Fouling factor is a factor which takes into account the thermal resistance offered by any chemical deposits that are formed on the heat transfer surfaces, both on hot side as well as on cold side. Therefore the overall heat transfer coefficient will be like this: 1 by U is equal to 1 by H1 plus 1 by H2 plus F1 plus F2, where the F1 and F2 are fouling factors. We also have the formula 1 by U dirty minus 1 by U clean is equal to fouling factor. U clean is nothing but 1 by H1 plus 1 by H2. 1 by U clean is nothing but 1 by H1 plus 1 by H2. U dirty is nothing but this. So what are the effects of fouling? What will happen because of this fouling? Because of this fouling, we are getting the overall heat transfer coefficient, or overall heat transfer coefficient will get reduced, because of which the overall heat transfer will also reduce. Therefore and also Ntu is proportional to U, therefore Ntu is also will reduce, effectiveness is also will reduce, and heat transfer rate reduced by falling, that I have already told you. Generally Ntu is 1.15 to 4. Ntu can never be greater than 18 practically. Capacity rate ratio is a ratio of m dot Cp smaller to m dot Cp larger. This is very much important in the formulas of effectiveness in case of NTU. We have two extreme values of this C, that is either 0 or 1. When one of the fluid is undergoing phase change, then m dot Cp is infinite. Therefore C will become 0. For any, if in the other case, when both the fluids are having same heat capacity rates, then C will become equal to 1. For any heat exchangers, the function, then effectiveness is a function of Ntu and C. For the case of parallel flow heat exchangers, effectiveness can be written as 1 minus e power minus of 1 plus C into Ntu by 1 plus C. For counterflow heat exchangers, 1 minus e power minus of 1 minus C into Ntu by 1 minus C into e power minus of 1 minus C into Ntu. These are the basic formulas for effectiveness in case of parallel as well as counterflow heat exchangers. Now again we have two special cases regarding the effectiveness, that is when one of the fluid in the heat exchanger is changing its phase. I have already told you the value of C is equal to 0 when one of the fluid is undergoing phase change. Since we substitute C in effectiveness equation, we will end up with this result, which is same for both parallel as well as counterflow heat exchangers. When both the fluids, cold and hot, have same or equal capacity rates, that is C is equal to 1, then in that case for parallel flow heat exchangers, effectiveness is 1 minus e power minus 2 times of Ntu by 2. But when you are writing it for counterflow heat exchangers, you will end up with 0 by 0 form, which is not acceptable. After applying L'Hospital rule, you will get Ntu by 1 plus Ntu. Now let us see how the problems related to effectiveness and Ntu method would like to be. The main objective of this method is to obtain both the exit temperatures of hot and cold fluids for a given heat transfer, that is given heat exchangers area. Here in the question, the heat capacity rates of both hot and cold fluid will be given, and you will be given overall heat transfer coefficient U, and only two temperatures will be given. But in case of Lmpd we will get 3 temperatures, but in case of Ntu only 2 temperatures will be given, and we have to find the remaining 2 temperatures. But here area of heat exchanger is already given. The only thing that we have to find is the 2 exit temperatures of the fluids. Solution is here. Calculate both the heat capacity rates, that is cold fluid and hot fluid, and compare which one is larger and which one is smaller, and find the Ntu using this formula, and obtain the effectiveness using effectiveness as a function of Ntu and heat capacity ratio, and then select only one formula of effectiveness. I have given you 2 formulas, that is simplified formulas. Choose either one of them and try to find that exit temperature only for one fluid using that effectiveness formula, and for the other fluid just apply the heat balance energy equation. You will get the temperature of the other fluid. This is how we will solve the problems related to Ntu method. Ntu method is more prominent than Lmpd method because this method can be used to design the heat exchangers without calculating Lmpd. Here we are not supposed to calculate Lmpd, which is a time consuming process. Without going to Lmpd, we can directly calculate the area, that is we can directly design the heat exchanger. In your next video, we'll be solving some of the problems related to LMTD as well as NTU so that your concepts get cleared. So this is the end for today's video. We'll see you in the next video. Keep learning, enjoy learning, keep practicing, don't lose your hope. All the best for your exam. Thank you.